To understand the basics of how a quantum computer works, we must first understand a regular computer's mechanics. Computers contain chips, which contain modules, which contain logic gates, which contain transistors. The transistor is the simplest form of a data processor in computers, which is basically a switch that blocks or opens the way for information coming through a computer. These transistors are similar to a circuit with a switch. This information is known as bits, which can be either set to a 0 or a 1. When you put multiple bits together, you get more complex information. These modern transistors are so small they're about 14 nanometers long, which is 500 times less than a red blood cell. Because these transistors are shrinking to the size of atoms, quantum physics helps us understand the different properties they have in the microscopic world. Instead of bits in a regular computer, quantum computers use quantum bits, also known as qubits. Qubits are not set to a 0 and 1, but could be any two-level quantum system such as atoms, ions, or the polarization of a single photon. For example, when qubits represent photons, the qubit could be in two states, horizontally polarized or vertically polarized. Qubits essentially perform the same task as a bit, working together as computer information. Qubits have a special quantum property called superposition. Superposition means that the qubit does not have to be one of the two states, but it could be in any proportions of both states at once. The qubit is in superposition of probabilities for 0 and 1, and we cannot predict which it will be. The instant you measure it, the qubits collapse into one of the definite states, 0 or 1. If you had 4 regular bits, you could have a total of 2 to the 4th configurations at a time, which is 16 different combinations, where you could only choose one. With the property of superposition, 4 qubits could be all of those 16 possibilities at the same time. If you have 20 qubits, you could already store more than 1 million different values in parallel. Another property qubits have is entanglement. This is a close connection that makes each of the qubits react to a change in the other state instantaneously, no matter how far apart they are. This property allows you to measure the property of one of the entangled qubits and deduce the property of the other qubit without even looking. Measurements of physical properties such as position, momentum, spin, and polarization performed on entangled particles have an opposite relationship with one another. For example, if a pair of particles are generated so their total spin is 0, and one particle is found to have clockwise spin on a certain axis, the spin of the other particle on the same axis will have a counterclockwise spin due to their entanglement. A normal computer has a logic gate, which is a combination of transistors designed to perform simple actions using zeros and ones. These logic gates obtain a simple set of inputs and produce one definite output. A quantum gate uses an input of superpositions and outputs another superposition. A quantum computer sets up qubits, uses quantum gates to entangle and manipulate the superposition, and collapses the superpositions into a definite output. Using qubits, the quantum computer can work millions of computations at once, while the regular computer today can only perform one at a time. Although we will not use quantum computers in our day-to-day life, there are many useful applications for them. One is database searching. A normal computer would have to test every single entry in a database to find something. Quantum computers use approximately the square root of the time it takes for a normal computer to search a database. With companies maintaining large databases, quantum computers can make database searching much more efficient. Quantum computers are also extremely helpful when testing simulations. Simulating microscopic-sized items such as molecules are very inaccurate when using a normal computer. The accuracy gained by quantum computer simulations are much more precise, which can provide insight to new molecules like proteins that have the ability to revolutionize medicine.